right, so I can tell you, let's see. You can tell which one's going to be easier, mesh or node, based on a couple bits of information. So here, this is what we'll do. I'll show you this. We'll put this in blue, take the arrow off. I had to restart my thing because I deleted it by mistake. All right, so how about this? This is what I'll show you. If you want to do mesh, you draw your loops. So we have one loop here, and one loop there. You see that?
Mm-hmm.
So that means you have 3 equations. Okay. This one doesn't have a current source. If this guy right here were a current source, then you'd actually only have 2 equations because that's the way mesh works. So with a mesh, you get 3 equations. With a node voltage, we got to count our nodes. So this is our ground. And then we have 1, 2, 3. So it's funny enough, you have 3 equations for the node voltage, but you already know that that voltage is 10. So you really only have 2 equations. So it actually looks like node voltage is going to be easier.
Okay.
However, this guy is not grounded, which means that we're going to have a, what are we going to have?
We're going to have a
Since
supernode.
Yeah, that's right. We're going to have a supernode. Exactly. And so this is just kind of how I analyze circuits. That's how I look at them. So if you're unsure about like which one's going to work, just kind of do what I did there. You look at how many loops you have for the mesh, and that's going to tell you how many equations you have. And then you look at how many nodes you have for the node voltage method, and that's going to tell you how many equations you have. So let's do node voltage first because it's easier, and then we'll run back through it with the mesh current method. Have you guys started that mesh current method in class?
No. So we've seen it a little bit in our lab, but not in the class. In my lab, he's going over Thevenin.
Oh, he skipped it. He skipped mesh current then.
No, he did. No, he did mesh, and he did mesh. He did mesh. Then he did node. Then he did mesh. Then he did superposition. Then he's on Thevenin in my lab. So he kind of goes over it like in a basic way, so you get like a general understanding. Because in lab, there's only very simple circuits that you have to solve. But then in the class, you get to have a better understanding because it's like he as a professor in the actual class is like super complex with his circuits, or the circuits are weird. You know, like he doesn't use supernodes in the lab. Like the person that does it in the lab doesn't do that. So it's like
he tries to keep it simple.
Yeah, he keeps it simple.
I mean, well, honestly, you're kind of doing your disservice because supernodes are an inevitability and they're not that complicated. A lot of students like to think of that one extra step as like this really complicated thing, but it really shouldn't. So the good thing is that we're gonna attack this, and we're gonna need a supernode. So we're gonna get our practice.
I mean, he just says like he just lets the actual professor who teaches the class go over stuff like that.
Yeah. All right. It's all good. Let's solve this bad boy. So I just want you to keep in mind that this is a voltage source because they told you that, and not go thinking that because it says current that it's a current source, because that's going to wreck a lot of students. So let's get to it. We're going to do no voltage method. The first thing we do, they label our ground. Our ground is here. We're good to go on that. Then we're going to label our currents. We already have IA drawn for us. I like to have my currents go toward the ground. So I'm going to have it go like this. And I guess based on the way that this is drawn, I guess I'll have this one go up through the 8, even though I would normally have it try to go down. So I draw my currents in. Then I'm going to label my nodes. So let's call this one up here node A. I'll put it in orange, I guess. So let's call this A. Let's call this B, and let's call this C. Cool. All right, dope. And so from there, now we've labeled our circuit and put all our pieces to put all the stuff together. Then we're going to take a look at what's the next step. Once we've figured all the circuit, like labeled all of this stuff, we labeled everything. So what we do next?
I mean, KCL.
Almost. That's the first step. That's the third step. Second step is this guy and this guy. You want to draft up, see how they affect the nodes automatically. So see how they pull everything together. So we'll do the 10-volt source. At the 10-volt source, that basically is going to tell you that VA equals 10 volts because you have the plus is on VA and the minus is on the ground. Makes some sense? And so it'll be the plus term minus the minus term. So it'll be VA minus VG equals 10, which just ends up being VA equals 10. Cool? So from here, we are going to take a look at our dependent voltage source. It's all good, though. It's still a voltage source. And so we're still going to do the same thing, put up an equation for it. And you're just going to say the voltage dependent, whatever. And the plus is on the C. So you put a VC. The minus is on the B. VC minus VB. This right here is the voltage across this guy. So VC minus VB. And then you know that it's going to be equal to 8I. So I'll put equals 8IA. Now, remember, when you're doing no voltage method, you don't want to have anything written outside of the no voltages. So IA can't be seen as IA. We're going to have to come up with a rendition for what IA is. But that's not a big deal. I just have to rewrite it. So we take a look at IA. You still with me, Mike? Oh, he left. Ah! I can't hear you. Let me see. Hold on. Let me see if I can pull you back on screen. Oh, no. It's okay. It looks like you're trying to get back on. I just sent you. Yeah, there you go. Perfect. I don't know.
I heard everything you said.
All right.
About it. I was talking. I didn't know if you could hear me.
No, I couldn't hear you. My bad.
Can you hear me?
I can hear you now.
Can you hear me?
Yeah.
Hello? Hello?
Yeah, I can hear you.
Hello?
I can hear you. Can you hear me?
Adios, mío.
Wait, don't leave.
Here. Hello?
I can hear you. Why can't you hear me?
Hello?
Oh, shoot.
Jeez.
This is bothering me. Can you hear me, Mike? Oh my gosh. Hello, hello, hello. The mic is working. It ain't me. I'll tell you that much right now. It ain't me. In a sentimental mood.
Oh, you could hear me. Okay, I can hear you.
Yeah. Can you hear me now?
Yep.
Good. All right. Let's practice. Get back on at it. I know you heard me, so I know we're talking about this guy. We're gonna rewrite him so that we can have it in terms of node voltages. That's all it's about, is rewriting things so that they are in the form that you need them to be. Cool.
Mm-hmm.
So we're just gonna say, okay, up here, IA equals, and so we're gonna come up with a representation for the current, and that's not a big deal. The current starts on B, and then it stops on A, and so it's gonna be VB.
Minus.
It starts. Yep. Minus VA. Is that it though?
No.
What else we got?
The resistor? No.
Yes, exactly, the resistor. So you have to divide it by 16. And that's what goes right here. So I'm just going to rewrite it one more time. VC. Hold on. I don't know what just happened. Did my screen just cut off?
It did, but I can see it again.
You can see. Can you see that?
I saw your home screen. I can't see anything now.
There it is.
I see it again.
I don't know why it just did that. That was weird.
I think it's just a technical difficulty type of day.
I hope not. I got a lot of work to do on this computer today. So we're going to do VC minus VB. Actually, I need that to be in green. VC minus VB. And then we put 8. 8 over 16 is going to give me a 2 at the bottom. So I'll do VB minus VA over, and this will be 2 because 8 over 16 is 1/2, right? Mm-hmm. And then we know that the VA is, of course, going to be our 10. Following me so far?
Mm-hmm.
Dope. So I'm going to leave that alone. I'm going to leave that as it is. And from here, I can keep on going. So I just did node A, and then I tried to do my dependent voltage source, but it gave me an equation that has two segments to it. So that's why we need our supernode. So basically we have to now do a node that does C and B all together. So let's do, I guess I'll put in a gray dotted segment. And so it'll be blah, 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 a little cloud around it. And so now we want to look at the supernode. And we'll do that. So bam, we're doing a supernode equation, and it's gonna look like this. So we got to look at our currents, right? We got 1, 2, those are our currents going into C. 3, 4, those are our currents going into B. You following me?
Mm-hmm.
All right, dope. So let's take a look at the 4 first. So first I'll do this guy. That's going to be VA minus VC over 4, and that's positive. Then I'm going to do this guy. That's going to be VC minus VG, which is 0, divided by 12, but that's negative because it's leaving. Then I do this guy. That's going to be VG minus VB, so just the minus VB, over 8.
Over 8.
And that's positive because it's entering. And then I have this guy, which is leaving, and it's going to be VB minus VA. And I got to divide him by 16, put that in parentheses so I don't forget to use my double negative. You follow me?
Mm-hmm.
Awesome. So from here, I just remember that VA is 10 and VA is 10. So now I have two equations, two unknowns. This guy and this guy. And so we just have to solve those. So let me see if I can clean it up a little bit to make it a little bit prettier. And from here on, it's just going to be doing straight algebra, okay? Everything up until now has been the circuits. We basically solved the circuit. With this, we've solved the circuit. Now we just got to kind of make do with what's happening here. So give me a second. Hold on. I'm sorry. Oh. All right. Yeah. So what we do is I'm gonna clean this one up first. Multiply everything by 2. That's 2VC. And then I get negative 2VB. I bring it over. That's going to give me negative 3VB equals negative VA, so negative 10. All right. So that's one equation. I'll put a 1 right here. And then this one moves over, and I got to multiply everything by, God, these ugly numbers. Why do they keep doing that? 16 and 8 and, let's see, 48. Yeah, 48 works, actually. So I'll multiply this whole thing by 48. So I'll put that on a little just marking. So I'll do times 48. So let's see what we get here. Put it in black. We get 48 over 4 is 12. So I get 12 VA, which is 120 actually. 120. Then I get minus 12 VC. Then minus 4 VC. Then minus, and then it'll be 5 VB, and then minus 3 VB here, and that'll be plus, and then 3 times VA, which is 30. It's funny because I actually I move faster than my computer can keep up, and so I got to do one more cleaning. Let's see, we got negative 8 VB, and we got negative 16 VC equals, that's going to give me a negative answer, so I'm actually going to make all of them positive. That's going to be 150, positive 150. All right, dope. So we have 2 equations and 2 unknowns, and so now we just got to add these together and figure out what we get, okay? Mm-hmm. All right, dope. So all right, see, it's at this point that it would be really, really nice if I had a calculator. So we're gonna combine these guys. And so let's see what I can do. I'm going to do 8 times the top, negative 8 times the top plus the bottom, which would give me 24 plus 8, which is 32 VB equals, and that's going to be 80 plus 150, which is 230. VB equals 230 over 32. And then VC is going to equal negative 10 plus 3 times 230 over 32 divided by 2. All right, so now I just got to put it in my calculator. Got to make sure I did the negative 8 properly. Negative 8, 8 times 3 is 24. 8 is going to be positive 80. Positive, you add those. All right, good. Yeah, looks like I'm in the clear. All right, so I got 230 divided by 32, which is 7.1875. I don't like it when they do weird numbers, but it'd be that way. 7.18. I'll do 188. And so that's going to be one answer. And then this is going to be, so what I do is I'll multiply that by 3. And then I do minus 10. And then I do divided by 2. That's 5.78. And with that being said, I just solve for VC and VB. So now I know VA, actually I'll move it over. VA equals 10. VB equals the 7.88. Move this over. Come on, I hate it when this does. See, I gotta go to a new program because it used to work a lot better than this. I didn't used to have these issues. Try this thing one more time. God damn it. All right, whatever. I'll just write it on the side. I'm gonna have to switch my program. VA equals 10. VB equals 7.188. And then VC equals 5.78. So we solved for the voltages on the circuit, but we didn't solve for the answer. Does that make some sense?
Yes.
All right. So why is this not working? Copy. Paste. And just delete this. It's bothering me. All right, dope. So, hold on. Excuse me. All right. So now we know the voltage across this. Now we know this guy. Does that make some sense? Because he's just going to be VC minus VB. So VC minus VB is the voltage of this is the voltage of the dependent source. So say voltage of the dependent equals VC minus VB, which is just going to be, so I got 7.188 minus my last answer, which is 1.4. So 1.4 volts is positive. Great. So now I know that this guy is corresponding to him. So we've solved for the voltage, but they didn't ask for that, right? They asked for the power. And so my question is, what's the equation for power?
Is it like I times current times voltage?
Perfect. Exactly. And so all we got to do now is say that, and I guess I'll put it in orange, whatever. No, you know what? I'll put it in this little stardust. I'll say power equals current times voltage. I have just solved for the voltage, right? So that's what goes here. So now we got to figure out the current. So my question to you is, how can we figure out the current? I want you to think about it because that's what circuits is all about. We got to think about how we can get that answer. How do we get the current? We got to solve for it somehow. Right? How do we get this? So whenever you're thinking about stuff like that, take a look at your circuit. Basically, you want the current that's coming out of this guy. The current's going to go like that through it. So that's going to be the current through the dependent. How can I find it? I'll tell you this. You don't know an equation that's going to automatically give you the answer for that current. So it's not like you can use V equals IR. Remember, V equals IR only works for resistors. And there is no equation for a dependent source that can give you the current. So how do you solve for the current if you don't know the equation of the current for that specific element? There's a way to do it.
I find the current going into. So find the current going into node B, and find the current going into node C, and then subtract the current going through B. Well, yeah, from subtract C from B.
Very close.
B from C.
You're very close. You're on the right track in terms of how you're thinking about the currents. It's just that you said the wrong statement to get the answer. So what you're saying is you find the current in B, you find the current in C, and then you subtract them from each other. That's a voltage way of thinking. But I like the track that you're on because it's similar to the current. All you have to do, if you don't know the equation for the element in itself, the only thing you can do is solve for the current using a regular old traditional KCL. And so that means you can do it at C or you can do it at B because the current going from B to C is ID. Does that make some sense?
Mm-hmm.
Which means that I can do KCL on B or I can do KCL on C and they have to give me the same answer. Whatever current is passing out of B has to be the current going into C. So I'll say solve for I into C or I out of B. They're going to be the same answer. Okay?
Mm-hmm.
All right. So with that being said, I'm going to do C. So I'll take a look at C and I'll say I have, and we're going to write all of the currents in terms of no voltage because that's all we know. So we'll say that's going to be the current in the 4 minus the current in the 12 plus the current in the dependent. And that's got to equal 0. And that's my KCL. You follow me?
Mm-hmm.
All right, cool. So that's my KCL. So now all I have to do is just rewrite everything in terms of no voltage form because I only have all my answers are written in terms of no voltage form. And so that's kind of all that I can work with. That's kind of my parameter set. So we're kind of stuck with using that explicitly, but that's okay. I4 I know is going to be VA minus VB over 4
Mm-hmm.
minus I12 is going to be VC over 12
Wait,
plus.
how is it VA minus VB?
I'm sorry, it's VA minus VC. I messed up. VA minus VC over 4. There we go. Does that equation make some sense?
Yeah, it does now. Mm-hmm.
And all I got to do is plug and chug. So I'm going to get ID equals VC, which was 5.78 over 12. And then it's going to be plus VC, which is 5 point. So I'll do 5.78 over 4 minus VA, which is 10 over 4. So whatever number that is. So let's go with it. We'll do 5.78. No, you know what? I'll do 1 over 12 plus 1 over 4 times 5.78 minus 10 divided by 4. That's going to be negative 0.573. All right, so this is shaping up pretty good, actually. So ID is negative 0.573. You follow me?
Mm-hmm.
And now I just plug that back into my I. And so, last but not least, I just solve for the power. And I can say power. I got to put it in my sparkle pen. Power equals negative. Remember, if power is negative, it's being delivered. If it's positive, it's being absorbed. So negative 0.573 times by 1.4. Let me move it over. And that is going to be our answer. So I do times 1.4, which is negative 0.8. And that'll be watts. And that is our answer. Boop. And I'll put a purple. That's that. You following me?
Yep. That makes
And
sense.
that's how you